Welcome to Peninsula Seniors Out and About. We're at the Western Museum of Flight in Torrance. Let's go see what Cindy has for us today.
Welcome everyone to the Western Museum of Flight. I'm Cindy Maka, the director. One of the characteristics of people who literally put their lives on the line to test new aircraft and aircraft systems is not only skill and dedication, but of course, courage. We're privileged to have one such courageous individual who not only faced the hazards of flight testing, but has experienced one of those rare but tragic events and survived to tell us about the loss of a prototype, one of the most beautiful in a long line of beautiful airplanes to come out of the North American aviation legacy. Ladies and gentlemen, it's my privilege to introduce Otto Wanacek.
Good morning, and thank you for coming to this presentation. I want to start off by saying thank you to the museum for putting this together and inviting me. And Cindy did a lot of work to make this happen, and I really appreciate that. And I think the forum is great, and it's great to see all these retired North American Rockwell people here. So I'm going to have to be real careful because they'll probably know more than I do. And then a disclaimer, I didn't write that introduction, I'm just me, and I will agree though that the B-1 was probably one of the most beautiful airplanes ever built, and it still is. It's a good airplane, it was in its early days, and it's still doing a great job today, even though it's been grounded temporarily for right now. But it always has been a beautiful airplane, always a favorite of mine, and not just because of what happened. So let me start by saying what happened. We were a young program, and I'll go through the history of the program in a couple of charts. But we had 4 prototype airplanes, and each one was called, as you can imagine, Ship 1, Ship 2, Ship 3, Ship 4. And the one that we lost on this particular day in August was Ship 2, and it was one of the first 3 airplanes, obviously, that had a capsule. It did not have ejection seats. It came off the line with a capsule, and the 4th A model, the 4th prototype, actually already had the ejection seats installed. So that decision was made long before the end of the A program and the resurrection of the B program. Just much cheaper, and from a maintenance standpoint, much easier to maintain. Anyway, the airplane we're talking about is on the screen. It's affectionately called by us Ship 2. It was used for flying qualities testing and ground load survey testing. Had a lot of instrumentation on board. By today's standards, you probably wouldn't say that's a lot, but back then, it was a lot of instrumentation. The crew was Major Dick Reynolds and Mr. Doug Benefield and myself, and it was a 3-seater. The capsule was actually designed for 4 seats, but because of the instrumentation installed, that 4th seat area was utilized by tape recorders, tape holders, and all the other stuff that goes along with making the instrumentation system work. So only 3 of us were on board. Good thing in this case, because later on up to 6 people flew in B-1s, and you can only imagine what that would be like if something went wrong. But we learned a lot that day, and that day started out as a great day. It was a beautiful August morning. We got up and had our crew briefing at 5 a.m. and went through all the briefings, and everything was fine, didn't have any trouble. Weather was great, and we stepped out to the airplane and did all our pre-flight inspections and started up and began taxiing. So the day started out great. Unfortunately, what started off to be a great day wound up to be a rather disastrous day. And the biggest tragedy was we lost a valuable test pilot by the name of Doug Benefield. Doug Benefield was the chief test pilot for North American Rockwell at the time. Great guy, really, like a teddy bear, big grizzly teddy bear, and fun to be around, fun to be with, and really, really an excellent pilot. He actually, before the B-1 program, did a tour overseas and flew the Concorde. So his portfolio of flying different airplanes was pretty broad and extensive. But he was definitely, chief test pilot material. He was the one everybody liked, the one everybody listened to, and it was a very sad thing to lose him, as well as a rather beautiful, pretty airplane. And what I want to do today is lead you through those events and tell you what happened, why it happened, and what lessons we actually learned from that event. We've passed those lessons on, and some of them are still intact today and being used by test programs. So from tragic things, often good things come. And I think when you see the airplane now and what it's developed into, if Doug were still here, he'd be very proud of the airplane that he helped get out into the field. Let me start with a little bit of history on the program. The actual program started out as a study back in 1962. The government loves to study things. And they studied things as to what kind of penetrator you would need to be able to contradict or battle the current threats. Back then, the Cold War was still alive and well. The XB-70 had been canceled because it was not considered a viable threat. And a low-altitude supersonic penetrator was the idea of the right thing for the time. So in 1965 or mid-60s, another study came in and validated all those results. And then all of a sudden, they said, okay, it's time. And a request for proposal went out to the contractors to find out what it would cost to build one of these airplanes and what it would look like and how it could function and what would happen. Well, North American Aviation was one of the contractors, and they won the award. And the contract was awarded back in 1970. And just note that date, 1970. Just keep it in the back of your mind. The first prototype, B-1A number 1, rolled out on the 26th of October in 1974. That's only 4 years. That's pretty good from a request for proposal, a contract award, and then an airplane, a real airplane coming out. And that airplane flew on December 23rd, 1974. The air crew at the time was Ted Sturmthal from the Air Force side and Charlie Bach from North American Rockwell. And to keep things simple, I'll just call it Rockwell from now on. So the Rockwell chief test pilot was Charlie Bach. He had a very impressive resume too, and the first flight was obviously from Palmdale to Edwards Air Force Base. Ted Sturmthal, some of the history buffs may remember, Ted Sturmthal actually flew the XB-70 back to Dayton, Ohio, where it's parked now in their museum. So he was a pretty active member in the bomber force. But that started the program. That was the first airplane. The first airplane was designated as the envelope expansion airplane. Number 2, the second airplane did the same thing. But the first one was tailored to do flutter testing. And that was, nowadays with all the modeling you can do, flutter is not as much of a factor, and all the structural secrets that you have working to build new structures can pretty much predict everything that's going to happen. Back then we had to test it, and the way we tested it, we used flutter wands, which were big masses installed in the wingtips, and those wingtip masses were driven up and down by hydraulics and then locked, and that would induce a load into the wing or into the stabilizer or the vertical tail. And it was pretty impressive watching the airplane doing its pre-flight, because before taxi they had to exercise all those systems, and you'd go out there and watch them, and these little wands with masses on the end would just swing and go faster and faster and then just lock. All that energy translated right into the structure, and you could see the entire structure just flex, and it was pretty impressive. And sometimes you wondered how that structure can take that. But we had it on the wings, we had it on the horizontal tail and the vertical tail, and those were used in flight to induce loads and monitor the damping of all the surfaces. So its primary mission was that, as well as expanding the envelope to faster speeds and gathering flying qualities data. So June 30th came along, 1977, and Jimmy Carter, he said he was going to do it, and he did it. He canceled the program. I happened to be on the program at that time, and I was a young second lieutenant, fresh out of college from the University of Washington, and my first assignment was the B-1A program. And here I was, 4 months, I got there in February, and 4 months later, the program was canceled. The only good thing about that was they allowed the airplanes to continue flying, and I think they flew until April of '81, and collect as much data as they could, and that data would be used for a follow-on effort. And at the time, we didn't know what that follow-on effort would be. But as things go, the follow-on effort was the B model, and the 4 prototypes were flown. They collected performance and flying qualities data. They collected avionics data and a little bit of defensive avionics data. So a lot of good things came out of those 4 airplanes. So when Ronald Reagan took office, he did exactly what he said he would do, and he resurrected the program. That was good news for us. In the meantime, since I didn't have a job in the Air Force, I applied to test pilot school and finally got accepted in '82 and went through test pilot school in 1982. And then, perfect timing, 1983 when I graduated, the program was starting up again, and I was able to request going back to that test program as a flight test engineer. And that's how I started out on the second time. I guess the first contract was going to build 244 airplanes, A models. The second contract that Ronald Reagan resurrected was only for 100 B-1 B bombers, and you know that was still good. And we started with doing some upgrades to the airplane. 2 airplanes were authorized. 2 of the A models were authorized to start flying again and start collecting data while they were building the first B-1B. And the 2 airplanes that were chosen were 159, which is the tail number of the one that was lost, and ship 4, which was actually 174. That 4th airplane was the one that I mentioned earlier, had the ejection seats, and it was quite a bit different than the first 3. As far as the air crew, Major Dick Reynolds was our newest Air Force pilot. He was being checked out for his final check ride, and Doug Benefield, being the senior pilot and chief test pilot, was checking him out. And they had flown together quite a bit, so they knew each other. But there was a big disparity between knowledge, because Doug was the senior pilot, the master, if you will, and Dick was a young major and new to the program. Had only flown with Doug in F-111s, but there was a lot of respect and admiration that went along with that. It was a factor that I'll discuss a little later in the decision, in the results. I was a captain at the time, and I think I had the most hours at the time, so I was considered the senior, not the old, but the senior FTE. And that was the makeup of the crew for the airplane that we were flying that day. Let me start also by showing you what the cockpit looked like. It's not exactly, by today's standards, a shiny speckling toy. It was old school. It was 60s, 70s vintage, so it had a lot of gauges that were mechanical and no displays that were electrical. But I'd like to point out a few things here. The first thing is the master caution lights. There was a master caution light located in front of each pilot, right at the top below the glare shield. That master caution light would come on when any of the annunciator lights flashed. I guess you could consider an annunciator light like an idiot light in a car, older cars. They would flash, trigger the annunciator, or the master caution, and the aircrew had to respond by acknowledging the master caution, pressing the button, and then we would troubleshoot the airplane depending on what it was. I was in the aft station. I had a CITS, a Central Integrated Test System, that was on board, and all the instrumentation, access to all the instrumentation parameters that were on board. So with using that information, we could pretty much troubleshoot a lot of things on the airplane. And then the control room was just a bonus at the time. They were looking out for us and provided extra information, and they also had all the engineering horsepower to make the decisions as to whether we would continue flying or come back home. So the annunciator panel is tied to the master caution panel. One of the things on the annunciator panel is the CG limit light. That was a light in the lower left-hand corner of that bank of lights that you see in between the knee wells of both aircrews. And it's squared with a red box, and on the lower left, note the location, no lower left, is the CG limit light. Okay, so CG was a big factor back then. We had a swing wing airplane that would swing its wings from 15 degrees forward to 67.5 degrees aft. That's a big change, and to accommodate for that, the CG had to be shifted so that you could maintain the balance of the airplane. And the way that was done was through an FCGMS panel, which is also highlighted on here. The FCGMS panel is the Fuel CG Management System panel. And this is a close-up of the Fuel CG Management System panel. Fairly straightforward. It has a vertical display. Going around in a clockwise direction, there's a vertical display of the percent MAC, and there's a little bar on the left side and a little bar on the lower right side, which were the forward and aft limits of the CG. In the middle of those is a bug on the left side and a little block on the right side, which was the target CG and the actual CG that the airplane used to calculate its settings. So when we were flying around, we would normally use the automatic mode or the optimum cruise mode. Now, all that meant was that the airplane was doing the work and keeping the CG between those two limit lines. So we also had a gross weight indicator, total fuel indicator, and fuel flow indicators. Fuel flow indicators were always impressive back then, especially when you used afterburners, because those engines really liked the fuel. And 30,000 pounds of thrust per engine takes a little bit of fuel. So that's how the panel was set up, and there were two systems. We could run system 1, system 2 for redundancy, or combine them both, and there was a voting plane that decided what the CG should be. But we're in flight test. In flight test, you don't check the nominal condition, you look for the extreme points. So all of our test points that we planned were usually done at a forward CG limit or an aft CG limit. So to balance things out, we almost scheduled every test point at a forward CG limit, at a mid CG limit, which was the optimum, and then an aft limit. So you essentially have 3 test points per condition. And to do that, you had to go to the manual mode. So a lot of times the switch was in the manual mode. I think it's called set. And as soon as you went to the set position on that switch, you could now dial a CG. There's a knob below those 2 wafer switches, and around the knob are the numbers for the percent MAC that you wanted, and you could literally dial the CG. And the way the airplane compensated for that was when you wanted the CG aft, fuel would be pumped from the forward tank to the aft tank. There was a 4-inch fuel line running from the front of the airplane to the back of the airplane. And that 4-inch fuel line transferred fuel and got us into the CG configuration that we wanted. Fairly simple. Just dial a CG, wait for it to happen, and press on. You're ready for the test point. So since we had this CG panel, let me review real quickly from the flight manual what the CG limits were, because there are a lot of CG limits for this airplane. We had a clean configuration, and it was based on wing sweep. And as you can see there, with the aft wing sweep, the CG band was pretty wide. That's at the top. It went from 25% MAC to 60% MAC. And then as you swung the wings forward, you got more and more constrained. And with the wing all the way forward, the CG band was a lot tighter, 10% to 27.5%. So you always had to be in the middle there. And if you set the optimum mode, the airplane would keep you in the middle. But we're flight tests, so we had to explore those lines and find out what it was like and collect data. So we were moving the CG all around for all the different test points. And one thing to note on this chart, on the top red line there, that was the test point that we accomplished right before the accident. And it was at a 55-degree wing sweep. The CG was set to automatic, or the auto mode, and the CG was at 45%, where it was supposed to be. And that's where we did all the test points. The chart on the right is the aft limit as a function of weight. As you can see, for the different wing sweeps, from 360,000 pounds down, you got the largest band. So we always used a fuel load of about, fuel weight of the airplane of about 355,000 pounds back then to take off, because that gave us the largest envelope that we could work in. So we would take off and then work in that envelope and then land, refuel if we had to, and then land when we needed to at the end of all the test cards. So the next chart now shows the CG limit that you have if you take your forward wing sweep and deploy the flaps and put the gear out, and the slats would be down. The band gets even tighter. The forward limit is still the same, 10%, but the aft limit now is 21% MAC. So if you're in the auto mode, the system would put you right in the middle. But we would have to, if we wanted to do the test point at the forward limit, we'd have to dial in 10%, or at the aft limit, we'd have to dial in 21%. Those are keys here also, because the second test point was with a forward wing sweep in the dirty configuration, or flaps and slats extended, and gear down. So we were in that tight band. And on top of it, it was a aft limit point, test point that we were going to do. So those two charts are key to showing us where we should have been, and now I'm going to show you how we wound up getting to where we were. Our test for the day, we had early morning takeoff scheduled with ground survey test points to do. That airplane, number 2, was instrumented, had gear instrumentation on it, strain gauges, and we were collecting loads, side loads on the gear. So we had the area in front of test ops cleared and taxied out and did our ground load survey testing, which was nothing more than just doing circles and going at faster and faster speeds, and then going the other direction. As you can imagine, a big airplane at 355,000 pounds, it was really hard on the tires. And after we finished those test points, we did get all those test points, by the way. After we finished them, the maintenance crew came in and took a look at the tires, and there were several tires scrubbed really bad, and 2 of them were way out of limits. So we were forced to go back and shut down while maintenance changed out a couple of tires. They did that, and they did that in excellent speed. You know, within 2 hours, we were called up again to go back out and fly the airplane. So they did a great job, put new tires on the airplane, and it was ready to go. So the next thing was we went back out and started out the airplane and taxied out, did the takeoff. It was a performance takeoff with a 9-degree pitch attitude. It worked fine, flawlessly. The airplane climbed out. No surprises. and we were scheduled to drop 5 Mark 82s. Those are 500-pounders. They were inert, and we were just going to drop them. They're dumb bombs, and we went to the PIRA, the Precision Impact Range at Edwards, to release those weapons. That PIRA is located just south of South Base, if people know where that is. And there's a big run-in line, and you drop you release your weapons, and usually score the target. So we did that. That went off without a hitch, no problems. And then we said, okay, next test point was to do airspeed calibration. And they wanted us to come by the tower flyby and check the airspeed. So we did a pass. I don't know if you guys know where the flyby line is. It's between the main runway and the tower. And the flyby tower is actually on the lake bed, or on the edge of the lake bed. And you fly by the tower, and they actually look at you to see your altitude, and you read your altitude and airspeed as you go by. So that was a way to check the airspeed calibrations. Did that, no hitch, and we said, okay, next point was min control speed. We were doing VMCA testing. We had specially designed those test points so they would be safe. They went through an SRB process, and the way they were done, we would put one outboard engine in afterburner, the other outboard engine in idle, and then use the 2 inboard engines to provide the thrust that you needed to maintain the speed that you wanted for your test point. Little bit of rudder pedal, as you can imagine, and the idea was you retard the throttles and slow to your test point, and as you slowed, more and more rudder was required, and when you got to max rudder deflection, that was the knock it off sign, and you'd recover the airplane. So that's how we tested minimum control speed. And as I said earlier, the first test point we did was at a 55-degree wing sweep. The next one was at a 15-degree wing sweep with the gear and flaps out. We never got to that second one. We were on our way to the second one when the incident happened, and we still had to do landing touchdown loads and braking effectiveness, so we didn't quite complete our mission for the day. But to go into some more detail as to what happened, I'll just put a picture of the airplane up, and it was a beautiful airplane. We were on Cords Road. That's where we did all our VMCA testing. And Cords Road, if you know where that is, it's just north of the field. It runs east and west from the Tehachapi Mountains to almost the end of R2515. And it's a long run-in, long line that you can do all kinds of testing on. Even the supersonic corridor is up higher, and very busy airspace at times. But we were flying back and forth on Cords Road, and you use that road as a reference. We were at 6,000 feet MSL, and Cords Road is probably 2,400 feet or so. I think we were probably about between 4,000 and 4,500 feet AGL at the time for the testing that we were doing. And we did the 55-degree point with the CG being in the nominal or middle of the band condition. And all that worked great. And we were done and recovered. And the control room called out and said, your speed brakes were out. We need to repeat that test point. So we did. We turned around and repeated the test point. A little embarrassed for having the speed brakes out, but put them in and did the same test point again. No issues. Everything was fine. So the next test point in the deck was the infamous test point, the forward wing sweep with a aft CG condition. So we were at 45% CG in the nominal or optimum mode and swung the wings forward. Just to let you know, the wings are swept by a lever on the right side or the left side of the cockpit, so the co-pilot or pilot can swing the wings. And it's just a lever that you push forward or aft on the side, and the wings are driven hydraulically to their commanded position. The idea was to, and in the flight manual, it also says you swing slowly and watch your CG. And when the CG goes outside of the commanded limit, you get the CG limit light on the annunciator panel. The CG limit light was down there on the lower left side of the annunciator panel, and it flashed a lot. Every time we swung the wings would move much faster than the fuel could be compensated for between tanks 1 and 4. So almost every time you swung the wings, you got a CG limit light, and you had to wait for the CG to catch up. And the pumps were working as fast as they could, and as long as you were patient and allowed it to catch up, there were no issues. So the issue we ran into was we swung the wings forward, and as you saw in an earlier picture, that limit light flashed, and Dick Reynolds, who was in the left seat, with his knee being right where it was, couldn't see it. He saw the master caution. Doug Benefield in the right seat, his field of view was not that far left to actually pick up that flashing light. But it flashed, it did exactly what it was supposed to, and the master caution light came on. The aircrew acknowledged the master caution light, assumed it was a CG limit lights, confirmed that it was, and we just, because it happened so many times, we just pressed on. Because it always flashed, and then within a few seconds to 30 seconds, it would go back out again. Unfortunately, this time it wasn't that way. So we continued setting up for the test point, and the wings were forward, the slats and flaps were out, the gear was dropped, and we had the engines in the configuration needed, and began to slow to the test point. The test point was at 137 knots. We were starting to slow, and all of a sudden, there was a slight nose rise. And both Doug and Dick had done high angle of attack testing before. They recognized that immediately and pushed forward on the sticks. And as soon as they pushed forward on the sticks, the nose started coming back down, which was anticipated. The next step was not. They pushed forward on the sticks, the nose came back down, and then all of a sudden the airplane just pitched up and went all the way up to 70 degrees. So when you were looking out the front, all you could see was blue sky. Very uncomfortable feeling in a big airplane. And the airplane pitched up, began to yaw and roll a little bit, about five degrees or so, and rolled right, left, right, and then started coming back down. The nose began coming back down. And Doug at the time called out that he thought we might be able to come out of it. Realistically, that was wishful thinking, because with a pitch up like that, you lose all your airspeed. The airplane was really not flying anymore. And right after that, Merv Evenson was the test pilot flying in the F-111, our chase airplane, called out and said, do you have it? Do you have it? And the answer was not yet. And at that point, literally the airplane sliced to the right and almost completely swapped ends. So we were literally almost facing the other direction. As that slice occurred, we were obviously falling like a rock because we had no more airspeed. To give you an idea of the timeline, from the pitch up to 70 degrees to us ejecting in the capsule was 29 seconds. And during those 29 seconds, both Doug and Doug especially and Dick were trying their hardest to recover that airplane. And Dick, after about halfway through, realized Doug was doing his best, and he started looking out of the window. And as you can imagine, we were not that high, and 4,400 feet or whatever we were above the ground gets eaten up real fast. And he could see the ground coming up, and since he was in the left seat, he was the one that initiated the capsule ejection. And before pulling the lever, he said, "We're going to have to eject. We're ejecting now." And pulled the handle, and the rest is history. So the capsule did its thing as well as it could, but the airplane continued on into the ground. And later on, on the data side, we found out that we ejected 1,505 feet above the ground. What that turns out to be, based on what the flight manual says, if we would have waited one more second, the parachutes would have never blossomed, and we would have never made it at all. So none of us would be here. And so we cut it close, and that was a lesson learned, and I'll go through those later. And the ejection process was pretty abrupt, violent. It made you realize how insignificant you are. As humans, we think we can do everything, but especially when we're young. But at that point, it's just forces that are in play, and you have nothing to do with it. And it throws you around, and the inertia reels that were supposed to fire did not fire. So the tops of our bodies were just at the mercy of all the forces. And the other interesting thing was, after that ejection, the capsule had separated from the airplane, but Doug was still flying the airplane. It's just ingrained. Your whole mission in life is to fly that airplane, and he did, all the way to the ground. Apologize, I still get emotional. The bad part was that the ejection seat, or the ejection capsule, didn't quite work like it was supposed to. What happened was one of the risers didn't release, so the capsule never uprighted itself underneath the canopies. And the way it's supposed to work, and I'll show you a video of that soon, is it was supposed to, the chutes blossomed, the capsule would upright itself, airbags would inflate, and you would land on the ground or in the water, and everybody would be safe and come back home. Unfortunately, because one of those risers didn't work correctly, the explosive bolt didn't shear, it didn't release, the capsule could never upright itself. So we impacted on the right front nose of the capsule. And the right front nose happens to be right where Doug Benefield was sitting. And his seat sheared, the adjustment screw sheared, and seat slid forward on the rail, went into the stick, and unfortunately his neck was broken, and that was all we could see at the end. After landing, Dick and I were able to talk to each other. We could yell to each other. We assessed our injuries, and at the time, Dick didn't want to tell me, but he already knew that Doug had passed. So we were there in the middle of the desert, laying there, and the chase airplane, the F-111, was orbiting. Dick blew out the left windshield and tried to wave at the chase, but the chase couldn't see him. The fireball that the rest of the airplane accomplished when it impacted the ground was so brilliant and strong that we were pale in comparison, because we were right next to the fireball. In fact, the chutes landed between us and the fireball, and they melted. So it was pretty warm. And I do vividly remember, because I was going to blow the back hatch, I vividly remember when Dick blew out his windscreen, all of a sudden the cockpit temperature went up by about 20 degrees. It just felt like an oven. And that quickly made the decision not to open any more hatches and wait. So we were stuck there, and I want to show you next what the airplane was doing as it went through that scenario that I just discussed. It pitched up to 70 degrees, like this little model shows, and it was yawing left and right and rolling right and left, and then finally, after the last roll, it just slides around, almost swapping ends, and right where it ends is where we ejected. Now, Bob Lee was the guy that put this together based on the Euler angles from the data system. So he was criticized for not having a B-1 airplane in there. So he redid it and made the airplane look more like a B-1. And it does look a little more spectacular if you look at that. But you can see on the right is the altimeter. And you can see how quickly we were losing the altitude. It's probably hard for you to see, but that little bug goes down pretty fast. And the airplane slices to the right. We had essentially no airspeed because we swapped ends, and the airplane was just going straight down like a leaf. A lot faster than a leaf, though. So we decided to eject. Dick actually made that decision, and thankfully he did. We went through the ejection sequence, and the next chart is from the flight manual. It shows how the ejection sequence should work. As you can see, it separates from the fuselage. There's rocket motors that ignite, frangible panels that separate, and the capsule comes off the airplane going straight up. And drogue chutes come out the back. They pull out the larger canopies. We had a 3-ring canopy, very similar to the Apollo capsules. So there were 3 70-foot round chutes that came out. And the drogue chutes would pull those 3 chutes out. And once the chutes were out, they would inflate and slow the capsule down. As the capsule slowed, it would swing underneath the canopy. And that's when the frangible panels or explosive bolts blew and allowed the risers to reposition themselves so that the cockpit would be in an upright position, and then the airbags would inflate and you would land on the ground, and then the chutes would just be separated so that it wouldn't drag you across the desert or across the water. So that's how it was supposed to work. Unfortunately, it didn't quite work that way for us. This is how the ejection is supposed to work when it works fine. This is a video from a sled test, and it all happens fairly quickly. You don't have much choice in anything that happens. It just happens, and you're just along for the ride and you hope for the best. Unfortunately, when we were in that position, we had just recently read reports of an F-111 where the ejection was unsuccessful, and it was because the chutes malfunctioned. So obviously that goes through your mind. But it happens so fast that you don't even realize that it all happened, that it's over. And your mind, a lot of things race through your mind, and all I could envision was that the chutes weren't connected and we're heading for the ground, and oh, this is going to be it. But it worked. It actually worked. We didn't quite land the way we were supposed to, and the next image shows that. We landed nose down. The airbags inflated, but they didn't do us any good because we didn't hit on the airbags. And it shows in the depiction here that we landed slightly to the right. If you look at the image on the right, you can look at the sand in front of the capsule that's laying in the desert. There's a little divot there. That's where the actual capsule hit and then bounced back. We hit with probably 40 Gs, maybe even a little more. And the seats inside were only designed for 40 Gs. And Doug was a little bit on the upper limit. And his seat, like I said earlier, the adjustment rod sheared and broke loose and impacted the stick and caused the injuries that were fatal. So that's how we ended that day, and it was not the ending that we had planned. So now what happened? Because we had a capsule, in one way that was kind of great. all the information was right there. From an accident investigation standpoint, this was ideal. You could see exactly what happened. Within minutes, we knew what was wrong. I won't say we. I didn't. Dick didn't. But all the guys that were scouring over the airplane came to the conclusion pretty quick. That FCGMS panel that I showed you early is pictured here, and you can see the forward and the aft limit bars at 10 and 21, right where they're supposed to be. But take a look at where the CG bug is. It's back at 45%. So it was very obvious. The switch was in the set mode, and that's on the right side of the panel, and the dial was set to 45%. So the airplane was doing exactly what it was commanded to do. It obviously was trying its best to fly, but only so much can be done. And it was pretty obvious real quick that we were after the aft limit, and we were unstable. Our static margin was probably almost 25% negative, and we were flying a very unstable airplane. So I've included Dick and I included some data traces. Back in those days, we used strip charts. I don't know if people remember what those look like now, but they were the instrumentation of choice back then. So we had strip chart data to look at, and this shows exactly what was happening to us over time. And at first you see the wing sweep, and the wing sweep was back at 55 degrees, and then we commanded it forward to the 15-degree point. There's a break in the sequence. That's just so that we could get it all together on one chart, because these strip charts were long, and we chose the right format to fit it all on one chart. But everything in between those two timeline events was just normal operation. The airplane was doing what it was supposed to do, and the wing was sweeping forward. It made it all the way forward to 15 degrees. The CG was coming forward a little bit, and that was because we swung the wings forward. A lot of fuel in those wings, so we swung the wings forward. And there was a time actually where the fuel pumps were compensating for the wings coming forward and driving the fuel back. But it was doing its job. It was holding 45%, which is what was commanded by the aircrew. So if you go to the right there, at 10:24 is when we ejected. Just before ejection, we had a 21% negative static margin. That means we were 21% after the aft limit. Interesting, the airplane was flying. We were on that upside down glass, the little olive there, and we were stable until we slowed down to the point and the olive rolls off the glass. And at that point, there was nothing else anybody could do. So airspeed, obviously, like I said, just disappeared on us, especially when the airplane swapped ends. There was nothing left of airspeed. And angle of attack correlates with the pitch up and shows exactly what you would expect. As far as the pitch attitude, this shows just before ejection, we hit 70 degrees pitch angle attitude. I have to admit, it was a scary sight. And I guess, I say that, and people probably wonder, well, how would you know? And because all the B models in the back, you couldn't see to the front. You actually had a console in the middle, a console on the left side and the right side, but the A models were different. The capsules just had a small console in front of the flight test engineer's position in the back, and it was really easy. I just turned my head. I could look at Doug sitting in the right seat. I could look at the panel that they were looking at. I could see what was going on and look out the front window, and it was very easy to see. So I did have that unfortunate firsthand experience. So why did the airplane fly as well as it did for so long? Well, we had a stability and control augmentation system that almost had full authority. So it was like an autopilot flying the airplane, and it was compensating for for the speed and deflecting that rear stabilizer up, 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 and more, almost, well, all the way to full deflection. The stick, because it was a full authority system, the stick never had the stick forces because it was taking out all the stick forces all the way. So you could see the stick forces. The pilot side was instrumented, and the stick forces were relatively benign until the pitch up, and then you can see both guys got on the stick, pushed forward, and tried to recover the airplane. So everything jived. The airplane was doing exactly what it was supposed to, and it was obvious that there was nothing wrong with the airplane, and it was just aircrew error. And that's how the accident went down. After all that, we did review things and we learned some lessons. And you always want to have lessons. And your hope is that those lessons that you learn, you can pass on to other programs so that other programs don't start from ground zero and sometimes learn the same lessons you did. So we always made it a point at the end of every program to write a lessons learned document, pass that on to the future program. And the B-1B lessons learned, B-1A lessons learned document that was written was actually used as a template for the B-1B program, or B-2 program, I'm sorry. But it was actually used for the B-1B as well. So it matured all the way through B-1B and then B-2. And I can attest that to be fact because I was the one that grabbed the document for the B-2 program, which I was on later on, and I used that B-1B as a template to create our lessons learned from the past for the B-2 program. So what other lessons do we have? Crew composition. That was the first thing you look at. Crew resources is a big thing in the Air Force, and how are you going to fly the airplane? Who does what to whom? What are you going to do? All of that is briefed up front in a crew briefing. We had our crew briefing. Everything was fine. But because there was such a drastic difference between the senior test pilot and the newer Dick Reynolds, Dick admired Doug. He was his mentor. They probably didn't do as much as they could. And this is conjecture. We did talk about things in the crew briefing, but Dick himself admitted that he probably should have been more willing to work with Doug, because on that day he was going for his check ride, his final check ride. So he was the trainee and Doug was the instructor. So they focused more on that. And not that it wouldn't have made a difference, but you always have to think, well, had we done it differently, it could have made a difference. So crew composition, because of the difference in talent and experience, was something that we passed on to future generations. And not that it's bad, but if you do have that condition, talk about it. Understand who does what when, and how are you going to take care of things. So that was the first lesson learned. Next lesson learned was test point sequence. We actually did a pretty dumb thing. We did an aft wing sweep point with a 45% CG and commanded the wings forward after that point, driving the CG to a forward location. So we set ourselves up. Had we done our test points in reverse order, it would have never happened. And we learned from that. We reviewed all the test cards for safety review purposes and made sure we had everything right. But not everything was reviewed other than the tests. So there's a lot going on in between test points. But in hindsight, when you look at it, if the cards had been flip-flopped, we could have avoided this. And so the sequence makes a big deal. And we at the time, we had a very senior flight test engineer from Rockwell by the name of Jim Leisure, and he was my mentor. He really knew his stuff, and conjecture again, had he put together those cards, it may have been in the other order. Unfortunately, he had just recently left the program, so there was a new mission planner in the office, and the guy was doing a great job, but it was just overlooked. It's real easy to Monday morning quarterback after the fact. So all these things come out, but when you're in the midst of everything and the program is go, 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 it's possible to make mistakes. So test point setup versus test execution. I'll go more into the SRB process. A safety review board has to approve all the test points that are flown at Edwards Air Force Base. All those test points that we accomplished were reviewed by the safety review board and given a risk level. This was not a hazardous test. The test point was easily accomplished. We had no problems doing the first one other than having the speed brakes out. The second one should have been no problem as well. The problem is the SRB process only reviews the test points. We were in between two test points. We were reconfiguring the airplane, and none of that was ever covered by anything other than pilot experience and air crews talking amongst each other. So because we were setting up for a test point, we were not under the same stringent rules that you would be while you're executing a test point. And as a matter of fact, on the ground in the control room, the engineers in between test points were discussing whether we needed to repeat any other test points. So while they were discussing that, all of a sudden the pitch up occurred, and everybody realized this was not normal, and they all made it back in time just to see those traces do exactly what they did. In hindsight, had we been watching the crew, had the crew been watching, had the engineers in the control room been watching the strip charts better in between the test points, it could have been caught. And we could have avoided that situation where we were 21% after the aft limit. So the next lesson was called warning fatigue. And I don't think that it's an official term, but it was used quite a bit after the accident. That CG limit light that I talked about earlier would flash all the time. And it got to the point where you almost ignored it. You expected it, it happened, it went away. So it was kind of ingrained in you to just react the way the aircrew did. They acknowledged it. It didn't go away, unfortunately, but they carried on, and they were anesthetized to what was really going on because it was so ingrained in them that the CG limit light would just go off, the CG would come back in limits, and there would be no problem. So it was called warning fatigue. It's that little light in the annunciator panel that kept flashing almost every time we swung the wings. And that was something that was written up afterwards as don't let yourself fall in this trap. If the airplane's trying to tell you something, listen to it. Don't ignore it. So this is the cockpit again, and it shows where that CG limit light is. And again, the knee of Dick Reynolds would be in that wheel well, or not wheel well, I'm thinking of cars, but the foot well. And if you imagine your knee being there and you're sitting in a seat, from your field of view, that little light is blocked. The only way to see it is you have to move your knee or look around your knee to see the light. So it's really easy to be conditioned to that warning fatigue factor. And as you can also see, that light is on the far left side of the panel, and therefore it puts it well out of the field of view of the right seater, the co-pilot, and that's where Doug Benefield was sitting. So he was reacting just like every other person would react. It's not in your field of view. You acknowledge the master caution. You know it's the CG limit lights. It's always on. You just press on. Cockpit and control room interaction. And this was kind of interesting because it's a resource management issue. We went and looked at data after the incident, and believe it or not, out of the last 65 flights on that airplane, we violated the CG envelope, FCG envelope, 47 times. That's why it was very common just to punch out that light and press on. Most of those 47 times was just 1 or 2%. And it was, over time, it was overcome. The pumps would transfer the fuel, the light would go away, and you'd continue on your test. One time it was this was the worst condition, obviously, but one time it was way out of limits. And the pilot flying at the time was Colonel Frank Burke, and he realized it, and he actually saved the airplane, because it could have happened to him, and let the airplane, the old trick, okay, God, it's yours. Let the airplane fly itself out of danger, and he just increased the power and waited for the CG to catch up. And by not aggravating or putting any inputs into the system, it was recoverable and flew out of the way. We had never talked about those incidences. You would imagine, the ground crew, the control room people saw it, they had the data. It was never talked about. The air crew had experiences. Actually, the Frank Burke's experience was probably the one that highlighted it first, because he was rather upset. And so we were kind of numbed to this whole thing. We never thought it would happen, and unfortunately, it does happen, and it did happen, and the results were pretty obvious. So having the control room follow you up is extremely important. Nowadays, the control room literally calls all the shots. The last program I worked on, the control room, they monitored everything all the time, and it was really refreshing to see that. I was the old head, the gray beard at the time, so it was really refreshing to see that our lessons learned were still being looked at, and the control room was 100% active all the time and looking at things. And when something didn't look right, we would cease testing and they would talk about it. The air crews had the same rights. If they saw something, they could say, okay, we're backing out of this until we figure out what's going on. And the B2 program learned a lot of lessons from the B1 program in that respect. So that was refreshing to see, and a good lesson learned that was passed on. As I said, we ejected at 29 seconds after the pitch up, 1,505 feet above the ground. So it was a delayed ejection decision. That was a criticism that came along with our accident. The Air Force regs are pretty clear. Uncontrolled airplane below 10,000 feet, you eject. We were never even at 10,000 feet. We started at 6,000 feet. So what we saw here was an air crew that was determined to do everything possible to try and recover that airplane. And fortunately, Dick was savvy enough. He'd done some parachuting before. He was savvy enough to see that ground rush thing that he knew about. And when he saw that ground rushing up, he made that decision to pull the handle. And fortunately, because of that, 2 of us are still here today. And yeah, me, for one. So it was a delayed ejection decision. Looking back at it, Monday morning quarterbacking again, when that airplane pitched up to 70 degrees, no matter what we did, wouldn't have made any difference. And people have asked, what's the fastest way to get the CG moving? And the fastest way was swinging the wings. But we didn't have that option. So even if we would have done that, there's no telling whether the airplane was recoverable. And most likely it wasn't, because the time it takes to retract the flaps, bring up the gear, it's all over. And then finally, the last lesson learned is it's a favorite. It's communication. Humans do not communicate very well. And it's sad to say, I don't know if it's our egos or what, but we will transmit, and other people receive, but they don't receive necessarily the same thing you transmit. And communicating is so important. You know, we saw these things, we didn't share them before it happened. You know, 47 times is a lot of times to be after the limit. And for that not to come up until just before our incident was really a bad on us. We should have done a much better job of communicating. Not to blame anyone, but the engineers in the control room, they had all that data. They saw it. Back then, they were analyzing all that data. We brought back recordings from the flight because we had onboard reel-to-reel recorders, and all that data was processed. Nowadays, because there's so much being recorded, thousands and thousands of instrumentation parameters, the only time it really gets looked at is if something goes wrong, and then they want to figure out why it went wrong. It's a simple fact. I couldn't even think of a better way to do it, but there's no way a group of humans, no matter how many, could look through all the data we generate these days and analyze it. It's just too much. They would be overwhelmed. And that trend is going to continue because we do more and more instrumenting now. And that just makes it more and more important that we communicate. So what the engineers see, they have to share with other engineers. What air crews see, they have to share with other crews. And passing that little tidbit of information on can make all the difference in the world. So we learned some lessons, we passed them on, and believe it or not, even after all this, the airplane kept on flying. The B model contract came out, the first B model came out shortly after the accident, and it was flown probably within 6 weeks of the accident occurring. I think, yeah, it was like end of September, and I know it was close because I was actually supposed to fly in B-1, B number 1 on first flight, and unfortunately I was not in the right condition to be able to do that. So it was great to see that the B-1B was alive and well and continuing on, and the program was successful. A lot of testing was done even after our incident, and a lot of data was collected. A lot of good things came from it, and we finally fielded the airplane in I think 1988. And in 1988, we thought, well, will this airplane ever be used? The B model was no longer supersonic at low altitude, but it was still a nuclear capable deterrent, and you know, you don't want to use it, but we all thought, would it ever be used? The beauty of it was that it was also a conventional bomb-carrying airplane, so it could do things like carpet bombing that the B-52 could do, and as time went on, the bombs got smarter and smarter, and JDAMs came along. The JDAMs were actually finally used in Iraqi freedom, where a B-1 actually went after Saddam Hussein. And that was one, I think it was in the news for quite a while. We got some intel that Saddam Hussein was in some high-level meeting, and the intel officers passed that on. A B-1 was airborne, a B-1B was airborne. It had JDAMs, GPS-guided JDAMs on board, and within 47 minutes, they were able to put 4 JDAMs on that target. Destroyed the target. It all worked. Unfortunately, Saddam Hussein was not there. So the system came out very good. It's an excellent airplane. I'll always be partial to it. I think Doug would have been extremely proud of the system, and I think he's probably still up there looking down at us saying, you guys did a good job. So that concludes the presentation, and I'd like to open it up to any questions that you might have at this point. Thank you very much. The question was, did I go back to flying status after the accident? And it took a while, and I think I was in the hospital for about 2 weeks. I had 2 collapsed lungs, a bruised heart, and broken ribs and several lacerations. So because of the bruised heart, they kept me in the hospital probably longer than I would have liked. But they were monitoring me, and it didn't stop me. I still got out. And about 4 weeks after that, after all the interviews, accident investigation interviews were over with, I went back on flying status, and the first airplane I flew was in a T-38. No problems. But I will say, the first time I got back into the B-1, it was the B-1B, number 1, and I didn't think nothing of it because I'd been flying F-4s and T-38s and didn't have any trouble. And when I got to that step ladder, all of a sudden my knees became very weak. And it was a strange feeling because all of a sudden I realized that this thing can hurt me. And but I did it anyway, and the B-1B number 1 was a 4-seater. It had the full cluster of instruments in the back, the offensive system and the defensive system. And because of that, you couldn't see forward, and that's why they had little windows on the sides in the back. We called them day-night indicators because the only thing we could do is open up the window and see a bright light coming in. So that was day. And if it wasn't daylight, you couldn't tell you opened the window. So, but there were several shots. I think it was Steve Harmon that was flying with me that time, and he took a camera, and he took a picture of me, and I had this glazed over look, like I was in shock. And I really wasn't, because I was actually busy, and that was the saving grace, because you're doing something. You're not thinking about those other things. And I survived it and flew a lot more times in the B-1. And even when we took B-1B number 1 to Dias during the deployment, I got to fly on that on the way back. So I got over it, I guess. It's a 2-part question. The first part, could we have done anything different to make it? And then the second part was, if we were at higher altitude, would it have made a difference? So the first part, could we have done anything? We looking back at it, and I think all the investigators came to the same conclusion, there was nothing we could have done. In the timeline that was there, there was no way to transfer that fuel faster, or fast enough to make the CG come. Had we realized it earlier, had we stopped the slowdown, but we were slowing down to get a test point, I'd have to say yes. But we were trying to achieve a test point, so that wasn't even in our mindset. We were going for a test point, and you know, if you didn't go for the test point, then yeah, it wouldn't have happened, and you could have avoided it. But as far as the other thing, if we were at higher altitude, we would have ejected. The same thing would have happened. The explosive bolt would not have sheared. That riser would have never released. So the impact of the capsule would be at the same angle. And we had fully blossomed chutes. I was only a second early, but we did get them, and therefore it comes out the same. My favorite maneuver, as far as a test point or just flying? Okay. Well, I was a flight test engineer, so I never legally got to fly the airplane. And but I think the things I enjoyed the most was low and fast. And also when you're in the pattern and you've got those 4 big afterburners, and you just pull back on the stick and watch that nose go up and turn into the pattern. It's a beautiful sight, and probably more spectacular from the outside than the inside. But that's my favorite maneuver from the outside. But from the inside, low and fast was extremely impressive. That airplane was designed to go low and fast, and it had little vanes in the front. They were called SMUX vanes, structural mode something system. They were little vanes that would deflect symmetrically or asymmetrically using sensors at different points of the airplane to undo the loads in the structure. And those vanes, when you engaged them, it was like putting on an autopilot at low level. It smoothed everything out. And I have to admit, the rush you get when you're about 100 feet off the ground doing almost 0.8 Mach, there's no feel like that. It's just unbelievable that a big airplane like that can do that. Did the stability and control augmentation system enable the airplane to go low and fast? And yes, it did. Because it had full authority, it was working 100% at low level to compensate for all the loads that were going into the airplane, as well as flying it pitch-wise and roll-wise. Because the airplane rolled with a combination of spoilers and differential horizontal tail. So pretty impressive airplane, still today. The question was, in the later days, in the B-2, did we see anything like the lights flashing on the annunciator panel and some of the other things that we encountered in the cockpit? And I assume your question would be, did we learn enough from that to not do it in the B-2? And the only way I can answer it, we didn't have any of that stuff in the B-2. The B-2 was fully automatic, and because it didn't swing wings, it had one CG band. And when you take the swing wing factor out of it, the airplane gets a lot easier to manage. And because the B-2, it's a solid configuration, it never changes. It gets its benefit by being almost neutrally stable, and therefore it can, well, maybe even unstable. Therefore it can do a lot of impressive things as well, but it requires a lot of computer power to be able to keep that unstable platform stable. And with the new avionics or new flight control systems that they have, that's possible. It wasn't possible back in the late 70s, early 80s. The question was, is the CG limits light that flashed audible? The master caution was audible. And anytime you had warning lights and you had caution lights, the warning lights were red and the caution lights were yellow. The CG limits light was yellow. And so, yeah, I'm not 100% sure. I can't answer your question totally, but I think the only audible tone I remember was the master caution that came on, because I actually had a master caution light in the back, so I could see what was going on. It was more of a statement than a question, but the rumbling and the power from those engines, 30,000 pounds coming out of 4 engines is unbelievable. And we did the same kind of thing at Edwards when they delivered the airplane to Dias. They took off, and then using the flyby line, they did a nice flyover at very low altitude, and just about where the flyby tower was, afterburners were engaged. So they came over the entire crowd in full afterburner and pulled up. Yeah. Beautiful, beautiful sight. You can only imagine how much fuel has gone through there. What was the design Mach number for B-1A and B-1B? B-1A was actually designed to be supersonic. It had a Mach limit of 2.2. Yes, the inlets, if you look at the inlets of a B-1A versus a B-1B, they're totally different. The B-1A inlets were designed for performance with movable ramps that would position the shock in the right place so it could go supersonic. The B-1B was more rounded for low observables, and it had potato chip vanes embedded in there that were not movable, so it almost made that airplane subsonic. So as far as speed goes, the B-1A model, we took it out, and the max number we got was 2.18. And that was, at the time, it was called WSMC, Western Space and Missile Center, off the coast of California. We were running between LA and San Francisco. There's 2 anchor points out there that you could station tankers. And we had to have tankers airborne with backups, and we would refuel to the weight required at one anchor point, then head to the other one, confirm that he was ready for us, and literally dive into the test point, and that's how we got our max speed. And the on-time condition was based on how much fuel we had left. So once you got to speed, and especially 2.18, we were only there for probably less than 10 or 12 seconds. You can imagine, that's full afterburner. All 5 flame holders were just bursting. The question was, what were Dick Reynolds' injuries? Dick was in the front left seat, and he actually had some pretty severe injuries. What happened, the inertia reels did not work, so the way the ejection was supposed to work, the inertia reels would fire, pull you back into the seat, and hold you there, and brace you for impact. Because his upper body was free, when we impacted, and because we didn't impact the right way, all the forces went into his spine. His spine, he had 3 lower vertebrae that were literally shattered. And that was his worst injury, and as you can imagine, that impacted him for the rest of his life. The good news is that they literally did, over time, rebuild him. They implanted a titanium ladder around his spine, and took the upper vertebrae and attached them to the ladder. The lower vertebrae attached him to the ladder, and then in the middle they built like a little squirrel cage and ground up some bone fragments and embedded that into the little squirrel cage and literally fused his spine together. What they originally did was just fuse the shattered bones, and he was in a lot of pain because he'd have pinched nerves, and that was what they could do back then. From the back side. The only way to do more was to go in through the front side, and it was years later that the pain finally got to the point where he was willing to do that operation. And they went in, did the ladder, and rebuilt his spine. And so about 10 inches of his spine was literally fused. And I talked to him afterwards, and he said he should have done it a lot sooner, because once he did that, almost all the pain was relieved. The pressure points no longer bothered him. He lost a lot of mobility and flexibility, but he said, I can still play golf, and that was important. Yes, and also, yes, and to recap his career, Dick Reynolds went on and finally retired as a 3-star general. He was the program executive officer for the B-2. Because of the Air Force rules and regulations, he was banned from flying in an ejection seat. The fear was that if he had to eject, it would kill him because of the fused spine. In the B-2 days, we worked on it pretty hard, and I think he, because of his position, worked on it pretty hard as well. He got permission to fly the B-2 bomber one time, and that was the one time he went back onto an ejection seat. And being the PEO at the time, not a bad stunt to do, if you want to call it that, but he loved the airplane, and that made our lives a lot easier on the B-2 program. So he went on to have quite a career, and he retired. He's now somewhere in the Ohio area. We exchange Christmas cards still, but one of these days I'm going to get back there and see him. I don't think he comes out here much. Oh, the repeat of the question was what was the lowest Mach, or the highest Mach number at low altitude? And really the lower, the one we used, I think the limit we had at low altitude, especially for terrain following, was 0.95. So we never went supersonic. Now the airplane, I think the B-1B, with its fixed inlets, could exceed that, but not by much. The question was, who were the initial cadre of B-1 test pilots? And at the time we were flying in the A model, there were 6 test pilots cleared to fly. Doug Benefield was the senior chief test pilot, also had Concorde experience under his belt. And Merv Evenson was the other test pilot from Rockwell, who became the chief test pilot after Doug passed away. There was a third one that I don't remember. As far as the Air Force side, Leroy Schroeder was a Air Force test pilot. Wayne Lutz was another cleared Air Force test pilot, and Dick Reynolds was getting his final check ride, so he was going to be number 6 to be checked out in the B-1A that we flew and lost. One other thing I should point out, that B-1A that we lost had a modified flight control system. It was not exactly what B-1B has, but it got us closer to telling us how well the B-1B would do. So we had some mods put in there, and we were testing those mods. The question was, is the escape capsule in any of the other production airplanes? And yeah, it was only in Ship 1, 2, and Ship 3. In fact, the 4th A model that was built already had ejection seats, and then all the B models had ejection seats. They used the ACES 2 system. And the reason that was done was it was a maintenance nightmare to refurbish all the pyros. That had to be done annually, and you can imagine what it takes to separate a capsule from a fuselage and do all that. So converting the seats was not only cost effective, but time effective as well. The question was, what caused the airplane to pitch up initially? And if you look at the data traces and all that, the SCAS system, the Stability and Control Augmentation System, was driving the rear tail up and up and up and trimming it. As soon as it got to its full authority, it was done. It couldn't do any more. And we kept on slowing down. So the tail, the horizontal tail, literally stalled, and the airplane pitched up. And with our FCG, that just made it all that much worse. The question was the impact on my career from the accident versus Dick Reynolds. Dick chose to stay in the Air Force. And after 10 years, I chose to get out of the Air Force. I didn't want to just walk away, so I stayed in as a reservist. So I have 10 years of active duty. I actually, when I separated, I was still a captain, and then I became a reservist. And in the 14 years of reserve duty that I did, I probably had one of the better jobs as a reservist. I got to teach at the Air Force Test Pilot School for reserve duty. So it was a great deal because I worked on South Base on the V2 program, and whenever I had to teach a class, I could just go to the bathroom like Superman, change into my uniform, and drive across base and go teach a class. And I did that almost all the way to the end of my Air Force career, when I went my 14 years there, and saw a lot of students go through there. Got to tell them this story several times, and talked a lot about instrumentation. And the one thing I noticed near the end, I was looking at all these students that I was lecturing to, and I said, these guys aren't old enough to fly F-16s. They looked like kids. And I didn't think I was that old, so. But it made me think, you know, we were all young once and full of vinegar and wanted to do everything. So it was kind of refreshing to realize that and see the newer generation going out there flying F-16s. They'll probably be flying F-35s pretty soon at test pilot school. So I stayed in for 14 years of reserve duty, and I retired as a lieutenant colonel. So. And then as far as the civilian side goes, I don't think there were any repercussions there. Probably got more opportunities there in the flight test field than anybody else would have. And I think that was primarily because of my experience. You don't get that kind of experience just coming out of college. And because of my history, I knew what not to do. And actually I could justify it because I said, this is why you don't do it, because we have proof that bad things can happen. So I took that attitude with me through the B-2 program, and then I worked at ATDC for a while and retired from ATDC. So now I'm just purely retired, and I get to play with my cars, and I'm working on an airplane, building myself. Thank you. Appreciate it.
Thank you for watching Peninsula Seniors Out and About. I'm Betty Wheaton. See you next time.